Okay, back again, Advent of Code 2022. Today is day 9. We've had a rough couple of days. If you go look at this, go here. Unfortunately, the past couple of days haven't been so great. I think both days, I initially went down the rabbit hole of not so great approaches and wasted a bunch of time on that. So generally, in like the first 2 weeks of the month though, there's a difficulty spike and then it goes back down. So I'm not exactly sure what's going to happen over maybe the next few days, but the latter half of the month is definitely where the problems start to get super tough. I think if I'm setting a personal goal for myself, it'd be to get to 1,000 points by the end of the month, or maintain top 50, whichever one that is. I'd be happy with that, honestly. With how tight the competition is, like it only gets harder and harder every year. And last year I only literally snuck into top 100 by getting 100th place. So given where I am now, I think a few good days in the rest of the month can boost up to 1,000 points, and I'd be satisfied with that. But yeah, hopefully just aiming for a mental reset after the last couple of days. Trying not to overcompensate and try to go like extra fast, because that's generally where more mistakes are made. Yeah, it's cool to see that more people are somehow finding the videos on YouTube. Compared to, I guess, some of the other YouTubers that I've seen searching them up, they're a lot more explanatory and kind of going through them, the problems after the fact. I feel like those are better to learn from, and my videos are more just about me uploading, me trying to solve them really quickly, trying to leaderboard. And I'm pretty scatterbrained at the end of it, trying to fit together the pieces of the pie, I guess, of what I just wrote. So, but I'm glad people are finding the videos somewhat useful. Let's just make sure we're all set up. We're day 9. We're looking at day 9 here. Alright. More of the images developing too, so it'll be fun to see what that turns into. Someone on the subreddit was like, I think there's a bug because this part of it is colored even though the day isn't open yet. So I wonder if this is meaningful somehow. The possible directions: up, right, down, left. Oh, the head starts on the tail. Okay, then it moves one direction so it remains close enough. Okay, yeah, fine. Always moves diagonally. Okay. So if they're in the same axis, we go, I guess, in that direction, right? Let me think. So can we move diagonally? So this would be north, east. This would be southeast. It's probably an easier way to do this. This is northwest, southwest, else. So one of them is equal. So the x's are equal, so we just move to the closer side. If so it's bigger, so we want to go north. We go east. It's gonna be kind of tricky. We get dragged, we're at 4-3, great. Then we go up 4, we go up. Oh. Why did we... Oh, I see. If we're touching, it's okay. Better? Oh, that's even worse. So they differ by... Okay, so this is the diagonal case. So if it's absolute head dot x minus tail dot x plus absolute head dot y minus tail dot y is greater than 2, and then this is. Oh wait, no, I think that's... wasn't this else just supposed to be... like this? No. Oops. So this is if we're diagonal, right? So that's fine. But then at this point, we moved up to 4-1, and so we shouldn't move. Oh, this is only in the case of diagonals. But we do move if we're in the same axis. I think we do this logic here in this case. I mean, that's closer. 3-0, then we get dragged in here. 4-1, 4-2, 4-3. We don't move. We get dragged up to 3-4, 2-4. We don't move, 2-4. Oh, interesting. So here, we shouldn't, the tail shouldn't move. Why was the tail moving there? I shouldn't move between this step and this step because we just... wait, down 1? Yeah, we went down to 5-2. And then we moved to 4-2, so this shouldn't have... tail shouldn't have moved. So why would the tail be moving there? We're just gonna... it's 1. I mean, we're close. So yeah, it's not that case. And so we're not here either, right? Down 1. Why did we trigger here? Oh, because... okay. Oh, here's a fun part too. This is a very fun part too. Okay. How long is our bridge? It's 10 things long. Oh boy. Okay. So let's let's say head tail like that. This logic is fine. Just return the tail. And then for 1 to 10 we do they update and lock stuff, I guess? Yeah, because they all update each other, right? So it'd be like bridges I equals bridges I minus 1, where we update it based on that's the head and that's the tail, something like that. And then what is the question actually asking us? The tail of the rope, so the last thing. So don't want to do that. Here's a larger example, wonderful. Yes, I did mean bridge, in fact. Hello? $36. Cool. Okay, well, wow, we improved our position on part 2. We almost snuck back into the top 100, but we weren't quite fast enough. Take a look at the leaderboard. Wow. They're incredibly fast solutions. 2-minute solve for part 1, and then fastest part 2 is, well, I'm surprised actually, 2 minutes to optimize that out. And yeah, leaderboard closed in about 15 minutes for this one. So I'm going to transition over to the time travel portion and jump 3 minutes in the future and then walk through the problem. Okay, we should be back hopefully. Hopefully the stream did an auto stop. I saw OBS was talking about that as part of the settings. I'm just trying to confirm we're actually live again. Looks like we are. So today's problem was really interesting, actually. I'm quite happy with it. Unfortunately, I struggled a bit too much on part 1 trying to work out what was going wrong, but we got there in the end, so I'm pretty happy. Okay, let's just introduce the problem, right? This problem is called rope bridge. So for day 9, we have a rope bridge, and you can kind of think of the rope bridge as, well, it's exactly like a rope bridge in real life, where it starts with it all kind of bundled up into one spot. But the rest of the bridge is kind of underneath it. And if you take the head of the bridge, so the front part of the bridge, and you drag it, at first the rest of the bridge won't move because it's too close to, like, the ropes give it enough slack and it doesn't move. But as you drag the head of the bridge further away, the rest of the bridge starts to follow along with it, right? So if I try to move the head over to here, the tail has to follow, right? And likewise here, if we try to move it down here, the tail follows as well. Now obviously this makes sense when it's in like axis aligned, but there's other rules here too, where if you were diagonally, that's okay. It'll just the rope bridge can be happy with its components being diagonally apart. But if it gets further away than this, then it will try to move diagonally to catch up. And likewise here, if we were already diagonal and the head moved further away here, the tail will move up diagonally to try to keep up with it. So that's the rules of how one segment of the rope bridge will follow the segment in front of it. So the question, the input of the problem, if we go look at the input, all it is a direction and then an amount that we move by. And so we basically have to simulate this bridge and count all the spots that the tail touches along the way. So if we scroll down, this is just demonstrating exactly how the bridge moves, and there's lots of useful information here to help debug what's going on. The tail kind of followed this path. It drew like a 3, in fact. And so that's all part 1 is asking. So simulate us moving the head and drag the tail along with it and count all the different distinct locations that the tail touches. And so ignoring some of the magic that's going on here, I briefly during the break just updated my code to be a little bit cleaner. All we want to do is iterate through the lines in the input. So for the line of the day, we grab the direction and we grab the amount, turn the amount into an integer, and then we want to simulate this in a stepwise fashion, because on any given single instruction, like move 4 to the right, the tail is going to touch multiple spots, right, along the way, and we want to keep track of all those spots. So we can't just like jump ahead and TP the teleport the head over to here, or I guess it'd be over to here. We need to do each step independently. And so that's what this is for, and we don't need the iteration variable here in, I guess, the amount given in the instruction. We want to basically simulate all the parts of the bridge. And so, whoops, here, for part 1, let's comment this out. So try to pretend this doesn't exist, and I guess I'll comment this out too. And we'll just say the head of the bridge starts at 0, 0. And this point thing is basically just a helper class I have. It's just a wrapper that has an X and a Y position and lets you do some fancy stuff like adding 2 points together. I pointed this out, in a previous video, but something kind of annoying in Python is if you have 2, it makes sense to represent like a point like X, Y like this. But if you have 2 points and you want to add them together to say generate an offset, if you do this in Python, it'll just append the 2 tuples together, and that's generally not what you want. So if you use the reason I like my class here is if you did the same thing with this point class and you add these together, it does what you would expect. It adds the X and the Y component separately. So that's the main convenience that this affords us. But other than that, you could have done this exact same math with keeping track of X and Y positions separately. So for each step in the instruction, what do we want to do? Well, we have to move the head by a certain direction. We want to move it, in the case that the direction is right, we want to move the X over by 1, right? If it's up, we want to move the Y up or down by 1, depending on which convention you want to use. When I'm dealing with these graph-based problems, I like using the mathematical convention. So positive Y moves in the up direction, like a graph on the Cartesian plane. Even though if you say had this as an array, if you're increasing Y and you're indexing to the array, you're actually getting lower in memory, right? Because the rows go like this. But regardless, just choose one convention and stick to it. It doesn't matter in this problem because all we care about is the unique positions it's visiting. And as long as you're consistent in your code, it'll work just fine, right? So I like using positive Y equals up. And so what do we want to do? Well, we have to convert, sorry, I don't have the input up anymore. We want to convert like this into what do I need to add to my X, Y positions to go in that direction? And that's solved by this fanciness. So I wrote this really quickly. all this is doing is, and I'll rewrite it here, is creating a dictionary where up is going to be moving 0 in the x direction, 1 in the y direction. Right, we want to move this way, 1 in the x, 0 in the y. If we're moving down, we're moving 0 in the x, minus 1 in the y. And if we move to the left, we're moving minus 1 in the x and 0 in the y. So this is our directional mapping. So we want to, we described this as before. So first, move the head in that direction, or in the given direction. So head will be, and we'll add a different point to it. And what's that point? It'll be, we look up this direction in this mapping over here. Here I guess I'll drag this down. So that'll move the head. Then what we need to do is update the tail. And so let's say the tail position is going to be equal to the output of this function called update. And I'll document this so it makes sense. Given a head position, given the current position of head and tail, return the new tail position. So this is going to be the rules discussed above. We need to encode that programmatically. But we'll just pretend it's a stub and we'll fill it out later. So the new tail is going to be update, and we'll pass it the head and the tail. Great. Then the last thing we need to do is add it to this, add the current location of the tail after we potentially have moved it to the scene array, so we can keep track of all the distinct locations that the tail has touched. Great. So that's the core loop of the problem. Now all we have to do is encode the rules for how the tail moves. And I think I did it a bit inefficiently because I ended up copying this and this. So I'm just going to take a little bit of time to think about if there's a better way to do it. So the interesting rules are, if we're apart diagonally and we're further than 2 away, then the tail is going to move diagonally to chase us, right? So that's what I was trying to encode here. So this is greater than 2. If this occurs, if we have moved diagonally away from the tail, and it is far enough for the tail to come and chase us. Great. I'm thinking maybe this code is redundant. Okay, I'm just going to real quick run this. Should be 13. Great. And then what happens if I comment this out? We still get 13. Okay, so that I had to debug while I was writing the code. This is completely useless. Okay, so if we want to compute, okay, so there's basically 2 cases to handle. First, we can handle this case. So if we're moving too far apart diagonally, that means we need to move the tail diagonally. And so how can we figure out if we're far enough away diagonally? Well, we assume that, and maybe this is a silly assumption, but if we're moving horizontally, step by step, the head is never going to get too away from the current tail because it'll always have come to chase us. Remember, at the end of any given iteration, the tail is always either touching us directly adjacent or diagonally, right? And so this case here, if the distance on the x-axis we are away plus the distance we are on the y-axis away is greater than 2, that indicates we're in this diagonal case, right? We've gone from this to this, so we are 1 away here and 2 away here, which sums to 3. And 3 is greater than 2. I think maybe we don't even need this, and it'll still work, but I'm not 100% sure. Yeah, okay. So this statement was redundant, but it was kind of just a a check in my head because I couldn't reason through the fact that this being greater than 2 always implied the diagonal movement, that I wanted to make sure we were far enough away on the x, and we weren't on the same x-axis or the same y-axis. That implies we're moving diagonally. But this is the diagonal case. This is the need to shift check. So in the cases that we are moving diagonally, I just basically check which direction we need to move in. Maybe there's actually a better way to do this, but in the moment, I just checked the 4 possible cases, right? So let's look at this case, for example. Let's say we are looking at this. Our x of the head is bigger than the tail's x, and the y is bigger than the tail's y. So we fall into this case. And what does that mean for our tail? Our tail's going to move diagonally 1 to the north and 1 to the east. So I had these things, this n and the e, those are just aliases for, this is just equivalent to this. So we move 1 to the north and 1 to the east, right? But with this, you know, now I can just rewrite it as this, right? We're going to move diagonally this way. And so let's just rewrite all of these for a bit more clarity, right? Here we're moving southeast. In this case, we're moving northwest, which looks like this. And in this case, we're moving southwest, which looks like this. So this covers all the cases where we're moving diagonally. Otherwise, we need to move, check if we're moving horizontally. So cases where this happens is if the distance we are away is, so here's something interesting, right? If we are diagonally apart like this, okay, let's say, oh, this is a perfect example. We're here. I need to find an example. Yeah, this example. So here, if we move our head up here, right, the tail isn't actually supposed to move, right? And we're at a distance of 2 apart from the tail. So how do we make sure that we don't actually confuse this case with this case where we're 2 apart and we should move the tail? Well, the easiest way I could think of it is check to make sure at least make sure that either we are on the same x-axis or the same y-axis. So this is what we're doing here. And then we want to make sure that we're far enough away, we're at least 1 apart. And then the tail will kind of slingshot towards us, right? And so this is just me comparing the distance, but you know, it could just be rewritten like, kind of like the first statement where absolute head.x minus tail.x plus absolute head.y minus tail.y is greater than 1. Yeah. So that covers this case, right? We're on the same x-axis, so head.x is equal to tail.x, and we're further than 1 apart. We're exactly 2 apart. So that falls under this case. I originally, if you saw while I was solving it, this condition wasn't firing when it was supposed to, and it's because I didn't have brackets around the or. And the way that it works in Python, if it's ambiguous, like A or B and C, the AND operator always takes precedence over OR. And so it was turning this implicitly into this. And this statement is very different from the statement we intended, right? This is saying if head is equal to tail.x, no, we don't even have to evaluate this. We always want to fire this condition. And so that's the problem that I ran into while implementing this. So let's put those brackets back where they're supposed to. So now we've checked that we actually are supposed to move the tail in either 1 space horizontally or 1 space vertically. And then let's just figure out what we need to do, right? If we're on the same x-axis, we have to update the y's. So here we can move north, and here we move south. And likewise, if the y's are the same, then we have to update the x. So if we are further away in the right direction, we obviously want to move the tail right to keep up. Otherwise, we want to move the tail to the left. Perfect. So that's a full implementation of how to update the tail given the position of the head and the tail. And that gives us the answer for part 1, right? If we run it on the sample input, we get tail sees 13 locations. And if we run it on the real input, the tail sees 61, 75. So part 2, rope snaps, ha ha ha, blah blah blah. But now the bridge, instead of being just consisting of 2 segments, it consists of 10 different segments. So as we move to the right here, you can see the rope bridge unraveling itself like this. And it starts snaking its way through and kind of crossing over itself like this. So on the surface, this seems pretty difficult, right? You have this kind of dance that the head is playing where it's like crossing over itself. This situation here where the head moves here, where's 2? Well, 2 is underneath of the 1, and here the bottom part of the bridge hasn't even moved at all. It's still stuck under the 6. So how can we efficiently simulate this, right? Just look at this, right? It's chasing itself around so much. And the question is still asking, how many positions does the tail touch? So the tail is going to be the S, I guess, at the very back of the, or sorry, I guess it's the 9, right? The very back of the bridge. And so the reason why we wrote this as a function is because it makes it really convenient. So instead of having an explicit head and tail, what we want to do is just define our bridge. And our bridge is going to consist of different parts, right? So here we'll say, if we want to simulate a bridge of length 10, we say this bridge is a list of 10 different points, and they all start at 0, 0, right? It's all kind of raveled up on itself here, like this. Then at every step, it's the exact same things. We first move the head, but then rather than only updating the tail, we want to update position 1 based on position of the head, then update 2 based on 1, then update 3 based on 2, all the way down the chain, right? Because in this case, over here, if we drag the head, the 1 will follow, then the 2 will follow, then the 3 will follow, and you have to kind of simulate the whole thing. So we update the head of the bridge, the 0th position, by the same amount. Then for the rest of the bridge, we update that position based on where the part in front of it is. And then all we have to do is add the location of the very back of the bridge to scene. And so if we run this, is my sample still copied? I guess the tail only sees 1 location for this. Oh, they gave us a bigger. We have to move the bridge a lot more. Otherwise, the 10 length bridge doesn't move at all. So if we run this, it says the tail visits 36 positions, which is what we expect here for part 2. And if we run this whole program on our sample input, or on the true input, we get 2578 here for part 2. So, you know, we're just using a bridge of length 2 for part 1, and then a bridge of length 10 for part 2. So yeah, that was day 9. A really fun question. Unfortunately, didn't quite sneak into the leaderboard because we're a bit too slow on part 1, but still a fun problem nonetheless. I actually really like this one, so I'm looking forward to see what the rest of the day has in store. Yeah, got 1/30th, so clawing our way back from a pretty bad day 8. So hopefully the improvement continues into day 10. But yep, thank you for watching, and I'll be back again